Tonight, when you step outside and look up at the moon, I want you to notice something. It is leaving. Not in a way you can see with the naked eye, but right now as you watch this, as the Earth turns beneath you, as the tides come in and pull back out along every coastline on the planet, the moon is moving away from us, silently, continuously, at a rate of 3.8 centimeters per year, about the same speed your fingernails grow. Over a human lifetime, the moon will be roughly 30 centimeters further away than it is today. You will never notice. No instrument you own can detect it. In the span of all recorded human history, every empire, every war, every civilization that has ever risen and fallen, the moon has moved less than the length of a football pitch. But give it enough time, and space has nothing but time. That 3.8 centimeters per year, compounded across billions of years, becomes something that does not just change this planet, it will finish it. Without the moon, Earth is not just a lonelier place. It is a fundamentally different world, one we might not recognize, one we might not survive. I'm Michael, a space researcher, and today we are going to follow the moon on its long, slow journey away from this planet. We are going to understand how it got here in the first place, through one of the most catastrophic events in the history of the solar system. We are going to understand what it has been doing for us invisibly every single day of the 4.5 billion years it has been here. We are going to stand at the edge of a moonless future and look at what waits there. And then we are going to talk about something almost nobody does when this subject comes up. This is the story of the most important relationship in the history of our world. And like all relationships, it has an ending. To understand why the moon is leaving, you first have to understand how it arrived. And the truth of that arrival is more violent, more improbable, and more remarkable than almost any story science has to tell. About 4.5 billion years ago, roughly 100 million years after the solar system formed from a collapsing cloud of gas and dust, something happened to the early Earth that should, by all reasonable expectations, have destroyed it entirely. Another planet hit it, not a rock, not a comet, not an asteroid, a planet, a fully formed planetary body, roughly the size of Mars, with its own iron core, its own internal heat, its own 50 million year geological history. Scientists call it Theia, named after the Greek Titan who, in mythology, was the mother of the goddess of the moon, Selene. The name is quietly perfect. Theia was not a visitor from far away. It formed in the inner solar system, close to the early Earth, and likely shared a nearby orbit around the young sun. For millions of years, both Earth and Theia grew as they collected surrounding space debris. However, the early solar system was unstable. The gravity of large planets, especially young Jupiter, slowly disturbed Theia's orbit. Over time, these changes brought Theia and Earth closer together until they collide. When Theia struck, it struck at an angle, which you can say is the luckiest thing that has ever happened to this planet. A direct head-on collision would likely have shattered both worlds completely. Instead, the angular impact did something different. The iron cores of both planets, being the densest material, survived the collision and merged. They sank together to the center of the combined wreckage and formed the large iron core that Earth has today. The same iron core that generates our magnetic field, which in turn protects our surface from deadly solar radiation. Another quiet gift from a catastrophe. The outer rocky layers of both Earth and Theia were extremely hot and melted. When they collided, pieces of rock and vapor were thrown into space and formed a large ring around the newly formed Earth. Unlike Saturn's icy rings, this one was made of hot, vaporized rock. Over time, the ring cooled down. Gravity slowly pulled the material together. Little by little, the debris clumped into larger and larger pieces. In just a few thousand years, which is a very short time in planetary terms, the ring came together to form a single spherical body. The moon. When the moon first formed, it was not where it is today. Current models suggest it formed at a distance of perhaps 20,000 to 30,000 kilometers from Earth's surface. Today, it is at 384,000 kilometers. It was, in other words, 10 to 20 times closer than it is now. And at that distance, it did not look like the gentle silver disk we see tonight. It filled perhaps 15 to 20 times as much sky. It dominated everything. It would have been visible even in daylight. At night, it would have cast shadows as sharp as noon. At that distance, the moon caused extremely powerful tides, not just a few meters, but hundreds of meters high. The early Earth was still partly molten, so the moon's gravity didn't only move water, it also pulled and stretched the planet itself. The surface bulged and shifted constantly as Earth and the moon orbited each other. It was, by any measure, an apocalyptic beginning to a relationship that would go on to make complex life possible. From the very first day it existed, the moon began to drift away. It has not stopped since. So why is the moon leaving? The mechanism is elegant. Once you understand it, you cannot unsee it. The moon's gravity pulls on Earth's oceans. You know this. Tides come in, tides go out. What most people don't think about is the geometry of those tides in relation to the Earth's rotation. Earth spins. It completes one full rotation every 24 hours. The moon, meanwhile, takes 27 days to complete one full orbit around Earth. The planet is spinning dramatically faster than the moon is going around it. And this speed difference is the entire engine of what we're talking about. Because Earth spins faster than the moon orbits it, the tidal bulge on Earth doesn't stay directly under the moon. Instead, it gets pulled slightly ahead in the direction Earth is rotating. rotating. This offset bulge then affects the moon through gravity. It pulls on the moon and gives it a small forward push along its orbit in the direction it is already moving. Here is where orbital mechanics does something counterintuitive. When you add energy to an object in orbit, you don't make it go faster. You push it into a higher, larger orbit. This is one of the genuinely strange truths of orbital physics, and it takes a moment to settle in. The moon, being continuously tugged forward by the misaligned tidal bulge, continuously gains orbital energy. And as it gains that energy, it migrates to a larger orbit, further away, slower overall, even though each individual tug accelerated it 3.8 centimeters per year, outward, always outward. Now, where does this energy come from? Energy cannot appear from nothing. Physics is very strict about this, and the answer is that the moon is not generating this energy. It is borrowing it, stealing it, really, from the one thing it has been coupled to since the day it formed, the Earth's rotation. As the tidal bulge pulls the moon forward, the moon exerts an equal and opposite pullback on the tidal bulge, which drags it slightly, creating friction as it tries to slow the bulge's forward motion. That friction acts as a brake on Earth's spin. Imperceptibly, day by day, the Earth's rotation slows. When the moon first formed, an Earth day was approximately 6 hours long, 6 hours from sunrise to sunrise. The planet was spinning 4 times faster than it does today. Over 4.5 billion years, the moon's gravitational influence has stolen enough rotational energy from Earth to slow that spin to 24 hours. And it is still slowing. Each year, Earth's day gets slightly longer, not by any amount a human can measure without atomic clocks, but measurably, consistently, permanently. Geologists have found ancient coral fossils, corals that record daily and annual growth, rings the way trees do, showing that 400 million years ago, a year contained approximately 400 days. The days were shorter. Earth was spinning faster. The moon's braking effect had already been running for 4 billion years and still had 400 million more years of work to do to reach today's 24-hour day. Every tide that comes in, every ocean that rises and falls, every time the water moves in response to the moon above, that motion is energy being transferred out of Earth's spin into the moon's orbit, the most patient energy transfer in the solar system, and it has been happening without pause since the day the moon formed. If you asked most people what the moon does, they would say something about tides, maybe the nightlight, maybe the fact that it looks beautiful. What almost nobody would say, because it is simply not taught, is that the moon has been running the background systems of this planet since before complex life existed, quietly, invisibly, without ever asking for acknowledgement. Let me show you what I mean. First, the moon stabilizes Earth's axial tilt. Earth is tilted. The planet's axis, the imaginary pole running through the north and south poles, leans at approximately 23.5 degrees relative to our orbital plane around the sun. This tilt is what produces seasons. When the northern hemisphere tilts toward the sun, it receives more concentrated sunlight and experiences summer. When it tilts away, winter arrives. The southern hemisphere experiences the reverse simultaneously. Without axial tilt, there are no seasons. Without seasons, the climate of the entire planet operates differently. The temperature gradient between equator and poles drives the atmospheric circulation patterns that distribute heat and moisture around the globe. Those patterns dictate which regions receive rain, which experience drought, which support forests, which support grasslands, which support the agricultural conditions that allowed human civilization to emerge 10,000 years ago. The tilt is not optional, it is foundational, and without the moon, it would not stay where it is. Computer models examining Earth without a large moon show that the axial tilt would not remain at a stable 23.5 degrees. Instead, driven by the gravitational influences of the other planets, particularly Jupiter and Saturn, the tilt would drift chaotically. Not a small 2 to 3 degree oscillation we see over 26,000-year Milankovitch cycles, but wild swings. From near zero tilt to potentially 85 degrees or more on timescales of tens of millions of years. An 85-degree tilt means the poles point almost directly at the sun for half the year. In that scenario, the polar regions receive more solar radiation in summer than the equatorial regions currently do. Ice caps melt entirely. Sea levels rise by an amount that would redraw every coastline on the planet. 6 months later, those same polar regions turn into months of complete darkness and cold that would make Antarctica seem temperate by comparison. The equatorial regions, meanwhile, experience something almost opposite: mild conditions for half the year, then extreme cold as the tilted Earth swings its equatorial zone away from the sun. The very concept of tropical and temperate climate zones breaks down. Mars has no large moon. Mars's axial tilt has wandered between near zero and 60 degrees in its geological history. Many scientists believe this instability is the reason behind Mars's inability to maintain a stable liquid water surface environment over billions of years, a factor in why Mars, despite showing clear evidence of ancient rivers and lakes, is today a frozen desert. Second, the moon drives the deep chemistry of Earth's oceans. Tides are not merely a phenomenon for coastal tourists and surfers. They are a planetary mixing mechanism. The rise and fall of tidal water brings enormous circulation patterns in the deep ocean. As its stirs nutrients from the seafloor upward, mixes warm surface water with cold, deep water, distributes oxygen and heat throughout the marine environment. This mixing is critical for marine productivity. The richest fishing grounds on Earth are not in the calm tropical waters, but in the upwelling zones, which are the places where deep, nutrient-rich water is pushed to the surface, often driven in part by tidal forces interacting with the ocean floor. These zones support the base of the marine food chain, the phytoplankton that produce approximately half of Earth's oxygen and support the entire pyramid of ocean life above them. A weaker tidal force means less vigorous mixing. Less mixing means reduced nutrient upwelling. Reduced nutrient upwelling means a less productive ocean. Less productive ocean means less oxygen production, a smaller marine food chain, and cascading effects throughout the entire biosphere. Third, the tides may have started life itself. This one is more interesting as science is careful about claims regarding life's origin, because we genuinely don't know how it happened. But one of the leading hypotheses for where and how the first self-replicating molecules formed involves tidal pools. In the early Earth, with the moon dramatically closer and tidal forces far more powerful than today, the rhythm of enormous tides would have repeatedly flooded and exposed coastal rock basins. Each flood brought fresh mineral-rich seawater. Each exposure allowed the water to concentrate through evaporation, increasing the density of organic molecules dissolved within it. The repeated wet-dry cycling provided the energy for complex chemical reactions that might not occur in a permanently submerged environment. Experiments replicating these conditions in the laboratory have produced amino acids, nucleotides, and other building blocks of life from simple starting materials. The tidal pool is not a confirmed birthplace of life, but it is a plausible one. And if it is the correct one, then the moon did not merely make complex life stable. It may have struck the spark that started life in the first place. Fourth, the moon paces biological time. Over the course of evolution, an extraordinary number of organisms have synchronized their most critical biological processes to the lunar cycle. This is not a coincidence. It is the result of billions of years of natural selection finding advantage in the most reliable, predictable environmental signal available. Coral spawning is perhaps the most dramatic example. Across the tropical oceans, hundreds of species of coral coordinate their mass spawning events to occur within days, sometimes within hours, of a specific full moon in late summer. The synchronization is so precise and so widespread across species that never interact with each other that it can only be explained by a shared ancient response to lunar light and tidal cues. The entire reproductive strategy of a significant fraction of the world's coral depends on the moon being where it is and doing what it does. Sea turtles navigate by magnetic field and return to natal beaches guided by moonlight. Fiddler crabs adjust their feeding activity to tidal rhythms with such precision that they maintain the cycle even in laboratory conditions with no tidal signal. The rhythm is internal, encoded over millions of generations of selection. Grunion fish in California beach themselves en masse to spawn on specific nights following full moons, timed so precisely that local humans gather to witness it as a predictable seasonal event. And then there is the human menstrual cycle, approximately 29 days, almost exactly matching the lunar month. Whether this is coincidental or represents a genuinely ancient synchronization is debated in science. But the fact that it is debated at all speaks to how deeply the moon has woven itself into the biology of life on this planet. Remove the moon, or move it far enough away that its light dims significantly and its tidal force weakens, and you remove a signal that tens of thousands of species have been using for longer than complex life has existed. Not quickly, the adjustments would take millions of years, but the disruption to timing, to the coordination of reproduction and migration and feeding that these species depend on, would begin immediately. Here is a dimension of the moon's influence that is almost never discussed outside of academic anthropology, and it changes the story from being about tides and orbits to being about something far more personal. The moon shaped us, specifically, directly, in ways that left traces in our biology and our culture that persist to this day. For the vast majority of human evolutionary history, and when I say vast majority, I mean something like 99.9% of the time our species and its ancestors have existed, there was no artificial light, no cities, no streetlights, no screens. At night, the world was dark, and the only meaningful variation in nighttime light came from the moon. On a moonless night, the African savanna, where our ancestors evolved, was dark enough that movement was genuinely dangerous. Predators that hunt by night, lions, leopards, hyenas, have visual systems adapted for low-light conditions that far exceed our own. In deep darkness, a human is at a severe disadvantage, vulnerable, hunted rather than hunting. Researchers studying traditional hunter-gatherer societies have documented this pattern clearly. Sleep data from the Hadza people of Tanzania, one of the last remaining populations living without artificial light, shows that sleep consistently shifts across the lunar month. People stay awake longer, sleep later, and sleep for shorter total durations in the nights leading up to a full moon. On moonless nights, sleep begins earlier and runs longer. This is not a cultural pattern. It is a biological one. The same pattern appears in indigenous populations across continents that have had no contact with each other. It suggests something ancient and shared, a sleep architecture that evolved in response to the moon's monthly rhythm. If this hypothesis is correct and it is consistent with the sleep data, then the moon may have been a reason for the very cognitive and social capacities that make us human. The ability to coordinate large groups, the ability to communicate symbolically, the ability to plan complex collective activities. All of these may have been sharpened over hundreds of thousands of years by a monthly window of moonlit opportunity that rewarded cooperation and punished isolation. There is also this. The oldest known evidence of human timekeeping is the Ishango bone, a baboon fibula found in the Democratic Republic of Congo, dated to approximately 20,000 years ago, carved with a series of notches that many researchers interpret as a lunar calendar. The oldest known writing systems include lunar notations. The oldest known structures built by humans, the megalithic monuments of prehistoric Europe, the stone circles, the burial mounds, are frequently aligned to lunar cycles with a precision that required sustained, accurate observation across multiple generations. The moon was not just a light in the sky for our ancestors. It was a clock, a calendar, a coordinator, the most reliable, most precise timekeeping instrument available to any human who ever lived before the invention of writing. The entire project of human civilization, agriculture, which requires knowing when to plant, navigation, which requires knowing position relative to the sky, religious practice, which in virtually every ancient culture was calibrated to celestial cycles, was organized in significant part around the moon. So we are not just physically dependent on the moon, we are culturally and cognitively shaped by it. While our moon moves away from Earth, there is a moon in our solar system that is moving in the opposite direction, toward its planet, faster every year. And studying it tells us what eventually happens when the relationship between a moon and its planet finally ends. Phobos is the larger of Mars's two small moons. It is not round, it is more like a lumpy potato, about 27 kilometers at its longest dimension. It orbits Mars at a distance of just 6,000 kilometers, extraordinarily close. For comparison, the International Space Station orbits Earth at about 400 kilometers, and Phobos orbits Mars at 15 times that distance. And because it orbits so close, something unusual is happening. Phobos orbits Mars faster than Mars rotates. This is a kind of similar situation of Earth and our moon, but in reverse. The tidal bulge Phobos raises on Mars runs behind the moon's position, not ahead of it. And instead of accelerating the moon into a higher orbit, this drag is decelerating Phobos, pulling it slowly, year by year, into a lower orbit. Phobos is falling toward Mars at a rate of about 1.8 centimeters per year. Not much, but enough that scientists can calculate with reasonable certainty what will happen and roughly when. In approximately 30 to 50 million years, Phobos will cross what is called the Roche limit, which is the distance from a planet at which the planet's tidal forces become stronger than the gravitational cohesion holding the moon together. Inside this boundary, the moon is literally pulled apart by differential gravity. The side of the moon facing the planet is pulled harder than the far side. The moon stretches, cracks, breaks. Scientists believe they are the first evidence of this process already beginning. Stress fractures. The moon of Mars is already showing the early signs of tidal disruption. It is cracking slowly under the strain of a gravity field that is beginning to overwhelm its structural integrity. When Phobos finally crosses the Roche limit, it will not fall to the Martian surface as a single object. It will be torn apart first, dismembered by gravity into a cloud of rock and debris. That debris will spread around Mars in a ring. Not as spectacular as Saturn's rings, Phobos is too small for that, but a genuine ring. A ring that will slowly, over millions of years, rain down onto the Martian surface as meteorite impacts. Mars, which currently has two small moons, will eventually have a ring, and then nothing. This is the other end of the story our moon is writing. Our moon is moving away, Phobos is moving inward. Two different trajectories, two different timelines, but both end in the same place, a planet alone without its companion. Our moon will not fall back, it will drift away, but the end point is the same kind of loss. The relationship ends, the partner goes, the planet is left to manage on its own. So what does Earth actually look like as the moon moves further and further away? Let us follow it step by step, because the changes do not all happen at once, they happen layer by layer. It is only when you see them together that the full picture of a moonless Earth takes shape. Stage 1, the tides quiet down. This begins now and continues indefinitely. As the moon retreats, its gravitational influence on Earth's oceans weakens proportionally to the square of the distance. Tides do not disappear immediately. The sun contributes about 1/3 of the total tidal force, and that contribution remains. But the dominant lunar tide vanishes. Coastal zones that have been rhythmically flooded and exposed twice daily for hundreds of millions of years experience less dramatic tidal variation. Intertidal zones, which are the strips of coastline between high and low tide marks, are among the most biologically productive in diverse environments on Earth. They are home to species that exist nowhere else, adapted to the specific rhythm of immersion and exposure, wet and dry, that the tides provide. As the tidal range shrinks, the intertidal zone narrows with it. The habitat compresses. Species that cannot not adapt to a narrower tide cycle, either move or disappear. This is not an immediate catastrophe. It is a gradual compression that will affect the food web in ways that are difficult to predict and impossible to reverse quickly. Stage 2. The nights go dark. As the moon moves further away, it subtly dims. However, it won't be like one night it will be all dark outside, but it will happen gradually. There is a brightness level below which corals spawning synchronization fails. A brightness level below which the navigational cues sea turtles use to find nesting beaches become unreliable. These thresholds are not all the same. They would be crossed at different distances over different timescales, but each crossing represents the loss of a synchronization mechanism that has been operating reliably for millions of years. A permanently dark night sky, dark in the sense of being lit only by stars with no lunar cycle, is not just aesthetically different. The organisms that depend on that signal do not simply switch to a different one. They face selection pressure that either forces rapid adaptation or culls those most dependent on lunar timing. Stage 3. The axial tilt begins to wander. This is the most consequential change, and it is the slowest one. The moon's stabilizing influence on Earth's axial tilt does not vanish overnight, or over a million years, or even over tens of millions of years. As the tilt slowly changes, the first signs are small and mostly statistical. Seasons start to vary a bit more from year to year, and long-term climate cycles become slightly stronger and less stable. Over tens of millions of years, the tilt drifts beyond the range that current life is adapted to. At high tilt, the polar regions receive intense summer radiation. Ice caps that have existed for millions of years melt. Sea levels rise by amounts that would submerge every coastal city on Earth and most coastal ecosystems with them. The species that depend on stable sea ice, stable permafrost, stable ocean temperatures, which is to say an enormous fraction of the life in the polar and subpolar regions, face conditions without precedent in their evolutionary history. Then the tilt continues to shift, swinging past the extreme to a new configuration, a different pattern of extremes. Every few million years, a new climate reality imposed by a tilting planet with no moon to hold it steady. Life adapts. Life has always adapted. The 3.5 billion year history of life on Earth is a history of adaptation to conditions that were, at various points, dramatically different from today. Ice ages, hothouse periods, ocean acidification events, mass extinctions. Life has survived all of them in one form or another. Microbial life would almost certainly persist through whatever a moonless Earth could produce. Simple organisms, fast reproducers, things that don't depend on stable seasons. But complex life, the kind that requires hundreds of millions of years of patient, stable conditions to develop, is more fragile than it appears. It is the product of unusual stability, and unusual stability on a moonless Earth becomes increasingly hard to maintain. The Earth without the moon is not dead, but it may well be alone. Here is the question that changes everything. How common is our situation? Earth is not unusual in having a moon. Most planets do. Jupiter has 95, Saturn has 146, even tiny Mars has 2. Moons as a category of object are common throughout the solar system and by extension throughout the universe. But Earth's moon is not typical. It is unusual in one specific way that matters a lot. It is large, disproportionately, strikingly, almost uniquely large relative to its parent planet. Our moon is roughly 1/4 the diameter of Earth. The ratio of moon to planet size in the Earth-Moon system is the highest of any planet-moon pair among the rocky inner planets. Scientists sometimes describe us not as a planet with a moon, but as a double planet, 2 worlds in mutual orbit around a shared center of gravity that lies just inside Earth's surface. Ganymede, Jupiter's largest moon, is bigger than our moon in absolute size, but relative to Jupiter, it is microscopic, less than 0.04% of Jupiter's diameter. Our moon is 27% of Earth's diameter. That ratio is in a completely different category. This size matters because gravitational influence scales with mass. A larger moon means stronger tidal forces. Stronger tidal forces mean more vigorous ocean mixing, more dramatic tidal pools, more powerful axial stabilization. The fact that our moon is as large as it is, the direct result of Theia being as large as it was and hitting at precisely the right angle, is what gives it the leverage to do everything we have discussed. A smaller moon would stabilize the tilt less effectively, would generate weaker tides, would contribute less to the geological and chemical conditions that made complex life possible. When astronomers study exoplanets, planets around other stars, and consider which ones might be capable of supporting complex life, the question of moons comes up. We cannot currently detect exomoons directly. Our instruments are not yet sensitive enough, but the theoretical work suggests that having a large stabilizing moon may be one of the conditions that separates worlds capable of sustaining complex life over billions of years from worlds that cannot. If that theoretical work is correct, then the universe may be full of planets in the habitable zone of their stars. Planets with liquid water, with organic chemistry, with all the ingredients we think life needs, that nevertheless fail to produce complex life because they lack the gravitational partner that holds everything stable long enough for complexity to emerge. We won the lottery, not once, but twice. First in the impact itself, itself, an event that should, by any reasonable probability assessment, have been fatal to both worlds involved. Second, in the size and angle and speed of the impactor, which produced a moon of exactly the right mass to do exactly what needed to be done. Every tree you have ever seen, every animal, every ecosystem, every human being who has ever lived, all of it traces back through an unbroken chain of causation to the moment a Mars-sized planet hit the early Earth at the right angle, 4.5 billion years ago, and left behind the debris that became our moon. Tonight, if the sky is clear, I want you to do something. Go outside, find the moon, and just look at it for a moment. Not with your phone out to take a picture, not while scrolling something else. Just you and the moon, the way every human who has ever lived has looked at it at some point in their life. What you are looking at is a world made from the wreckage of two planets colliding, a world that assembled itself from the vaporized remains of a catastrophe that should have ended everything before it began. A world that has spent 4.5 billion years drifting away from us, 3.8 centimeters at a time, slowly transferring its energy into our past, shaping our days, our tides, our seasons, our sleep, our biology, our sense of time itself. Every human civilization that has ever existed looked at the same light. Every calendar system ever devised was calibrated to it. Every ancient monument significant enough to survive thousands of years was built in alignment with it. The first human who counted the days between full moons and scratched the number into a bone, roughly 20,000 years ago, in what is now Central Africa, was doing the same thing you are doing right now. Paying attention to the most reliable clock the sky has ever offered. The moon is 3.8 centimeters further away today than it was this time last year. By the time your children are your age, it will be another 3.8 centimeters further, and their children after them. And every generation for as long as this planet continues to exist and the moon continues, its slow goodbye. But knowing it changes something, or it changes something for me at least, it makes the moon less like furniture, less like something permanent and assumed, not worth a second look, and more like what it actually is. Something that is, in the most literal, physical, measurable sense, slowly saying goodbye. We live in the window, the long, improbable window between the moon's violent arrival and its eventual disappearance from meaningful influence. A window that has already lasted 4.5 billion years. A window that has billions of years still to run. Look at it while it's here, because here is the thing about windows. You only ever appreciate them fully when you understand that they open, and that someday, eventually, they close.